All right, we're going to take a look at a former final exam problem. It's been used a couple of times, and I'll just comment, it's never gone very well. So let's see what we can learn from this. I have a car right here, and this door is, picture this door is slightly ajar. And the driver isn't aware of it, and they start accelerating back quickly, so that their acceleration as they back up is 11 meters per second squared. Well, I think you would all know from just imagination that what's going to happen is as you accelerate, this door is going to fling open. And the question is when the door gets to 90 degrees, that'll be right along here, what are the reactions at the hinge when it gets to that? And we're told when it gets to that 90 degrees, the angular velocity is 14.83 radians per second. So that's given. And we're also given some other information. The door, it's rotating, it has mass. So we're given its mass. We're told where the center of mass of the door is, 0.4 meters out from O. And we're given the radius of gyration. So with mass, radius of gyration, we can determine the mass moment of inertia. So we need to think how we're going to start this. And so the first thing we'd want to do is, since it's not given in the problem, is decide what we want our coordinate system to be and draw a free body diagram. Now, looking at what the problem is, you're definitely going to be dealing with, you got angular velocity, there's going to be acceleration involved, you're being asked for the reactions. This looks like a Newton's problem, okay? Now, maybe I should just take a moment and say, what are some of the reasons people struggled with this problem? And quite frankly, one of the biggest problems we've seen people have was this word reactions. And because people were just, they saw the word reaction and go, what does that mean? Well, let me just translate it for you really simply. If you see the word reaction, it means force. What are the forces at the pin, for the pin hinge at O? That's all it's saying. What are the forces at the hinge? Okay, so that's what we want to figure out. So let's, we have the solution here. And so I'm taking getting this set. We're going to take the usual coordinate system. And let's just, here we go. Put my hand there. So here's the free body diagram. So there's the hinge, will be at O. And so the car is accelerating back at 11 meters per second squared. All right. So at the hinge, we know exactly what the hinge is accelerating at. This. The hinge is fixed to the car, so we know what its acceleration is. The door has its own behavior, though it's driven by that. All right. So we take the hinge away. And I'm just letting the forces, I'm assuming the forces go in the positive x and positive y direction. When you solve for the numbers, you'll see if that's right or wrong. In general, when I do my free body diagrams, if I don't know it, I take it to be in the positive direction. So I'm going to assume here that I'm having positive alpha. Now with the door accelerating out this way, I know I'm going to get a negative alpha, but it's just easier for when I go to do any vector work. Okay, so here the door is in the 90 degree position. I know the angular velocity. Here's g, 0.4 meters down. And it's time to solve this thing. Well, if we look at it, we can solve forces, some forces in the x and the y. There are only two forces here. G is going down, all right? And the door's not falling off, so we don't even have to worry about gravity. So if you look at just in the plane of the door, what you see here, there's the xy forces in the hinge. The z forces, they don't matter, okay? Just two forces. So we can sum the forces in the x and the y, really very straightforward. And then we can also, we can do a sum of moments, and we'll do that at g. So let's just look at the sum of the forces. So there's just two, Fox, which is along the x, F at O along the y is simply ma. So we have the mass of the door, which we know, acceleration of g in the x, acceleration of g in the y. Okay, this is the only forces on the door. So if we look at that, now we can break this thing down further. So let's see what we can get here. I'm going to break down the acceleration at g. Now here we just said agx and agy, okay. But let's think about this. O is accelerating at 11 meters per second squared in the positive x direction. We know that. So g will be acceleration at O plus alpha cross r minus omega squared, our usual equation. That's what I have here. All right, so the acceleration at O is 11, and then you'd have alpha cross r from O to g minus omega squared r from O to g. Now r from O to g is simply minus 0.4 y. That's what we got from, let's bring this back down a little bit. All right, g is 0.4 meters down. So if you take alpha across r, now we were taking alpha to be going counterclockwise, it's quite apparent that alpha cross r would be going in the positive x direction. All right, so that's why it says 11 plus alpha times 0.4. We're going to find that alpha is negative, and that simply means it goes the other way, but that's fine. Then we have minus omega squared r, but r is negative, so that gives us plus omega squared, which we know, times 0.4, r 0.4. So there's that. Okay, now if you look at this, what we see here is that the f(x) is equal to this side, mass times this. f(y) is mass times this term. Well, we know the mass, we know this term, so we can get the y component of the force right now. We don't have to wait. Boom, we've solved for it. So we have this term times 15 equals f(y). So we have 1,320 newtons roughly. So now we look where we are. f(x) is an unknown, alpha is an unknown. So we have two unknowns, we need one more equation. So for that, we're going to go and take the moments at g. And that is going to equal, because it's moving, ig alpha. So that'll give us an equation with alpha. That'll take care of our problem there. So here we are. We're going to take the moments. It's equal to ig alpha. That's going to be the mass moment of inertia at the center of mass is 15 times the radius of gyration squared. So 15 times 0.2 squared. And alpha, and again, we're assuming alpha is counterclockwise positive. We'll just let the signs tell us otherwise when we go through it. All right. Well, so let's see. We have, when we take the moments, so we have f(x), and here's r this way. So that's going clockwise. So minus f(x) times 0.4 would equal this thing on the other side. All right. There's the alpha. Well, what I'd like to do is just get this down to one unknown. So I can replace f(x), right, with this term here. Mass times 11 plus 0.4 alpha. So that's what's right in there. So I'm replacing f(x) with mass times acceleration. That leaves me with one unknown, and I can solve for alpha. It's minus 22 radians per second. So looks like a pretty big number when you consider that a circle is 2 pi radians. That's really whipping around a circle fast. So it's going quick. All right, accelerating rapidly. Okay, so minus 22 radians per second squared for alpha. Sticking alpha in, we get f(x) is 33 newtons. Done. The key to this problem is one, when you see, we'll just take this down here. When you see the word reactions, it means force. Do not let it bother you. Okay. Secondly, coming up, when you do a problem, the most important part of this problem was doing a free body diagram. And noting that what the hinges are doing is simply 11 meters per second squared. So then we can simply use relative motion analysis to get an expression for acceleration at g. And then it's just a matter of summing forces and moments. You only had two forces here. It's really a straightforward problem. So we're going to end this video right here, and I'll start few more problems that are kind of meant for review as we wind down this topic. I'll talk to you again soon.